Hello, and welcome to Physics for Play. In this episode, we're going to be looking at coupled oscillators, which are oscillators that are connected together. Let's get started. So we're going to look at the motion of two coupled oscillators. We'll do a variable transformation that makes the physics quite a bit clearer. And then we'll talk about how to solve the system more generally using something called normal modes and treating it as an eigensystem. And lastly, we'll cover some of the things that you can take your own time to play around with and come up with your own theories and test a little bit. So we're going to start with a system of coupled oscillators, and that system looks like this. So what you have is you have two masses, mass 1 described by position x1 and mass 2 described by position x2. And there's some equilibrium position for those masses, and we're measuring the displacement off of that equilibrium position. But our system is different than anything we've seen before because the two masses are coupled to each other. So not only is mass 1 attached to this green wall with a spring, it is also attached to mass 2 with a spring. And this spring couples the motion together so that energy can transfer from mass 1 to mass 2 because it can pass through this spring. So we want to start with writing down the equations of motion for this system. So if I look at the force on mass 1, that'll equal the mass times the acceleration of mass 1, x1 double dot, or double prime. Now, if let's clamp down mass 2 and not worry about it just yet. But if I clamp down mass 2 and move mass 1, you can see I have really two springs that are pushing on it. I've got the spring on the left with stiffness kappa, and I've got the spring in the middle with stiffness kappa sub 1, 2. So I am going to get the total stiffness, I just add those two together. So if these were, both had the same stiffness, I would double the stiffness of a single spring. All we're doing is adding that two together, and then it behaves pretty much like Hooke's law. You get minus a constant, in this case, the constant is kappa plus kappa 1, 2, times the displacement. And everything's hunky-dory. That's just Hooke's law. But then we've got to deal with the fact that this other mass can also move. And if it moves to the right, well, it's going to try to drag mass number 1 with it. And if it moves to the left, it's going to try to push mass 1 to the left. So whichever direction x2 is in, whichever direction mass 2 moves in, spring kappa 1, 2 is going to be pushing back with an equal and opposite force that mass 2 feels. And so mass 1 is going to feel a force if mass 2 is moving. So we just write that as kappa 1, 2 times x2. And you can write down the exact same equation, but with the 1's and 2's reversed. So the force on mass 2 is equal to the mass times the acceleration of mass 2, which will have a Hooke's law type force with all the springs connected to mass 2. And it will also depend on how I move mass 1, because if I move mass 1 to the right, then the spring is going to push mass 2 to the right as well. So we can simulate that. As we have done many times, we were going to set up our, we'll go ahead and set up our parameters. So we'll define the mass. We'll define the spring constants of the outer two springs. We'll define the spring constant of the middle spring. I'm going to start by setting it equal to 0, just to go with the simplest case that we know. I'm going to use the numerical differential equation solver. You could use regular old DSolve for this to get an analytic solution. I'm just going to stick with numerical for now, just because it'll keep things. I don't want to change it. I'm lazy. And then we'll get our graphical output. So we'll make a plot, and we'll show an animation of the system. So as always, let me just hold it here in case anybody wants to pause the video and try to recreate the graphics that we've had. And if you want to recreate the animation, I'll scroll down and you can just copy this as well. So let's go ahead and solve our differential equation, get our graphical output. We'll do that. And you can see, oh, I forgot to point out our initial conditions. So in this case, our initial conditions, I'm going to start by displacing mass number 2 by a small amount, by 0.1. And I'm going to keep mass 1 at its rest position. And I'm going to give them no initial velocity. And you can see if you do that, mass 2 will oscillate, nothing will happen to mass 1. And it's because I have set the coupling spring, so the spring in the middle, I set that stiffness to 0. So it's pretty much like there is no spring there. So we can visualize this. You can see mass 2 is oscillating, nothing happens to mass 1. Again, because it's like that spring in the middle is not even there. Now let's see what we can do by just giving this, giving some amount of stiffness to the spring in the middle. So now we're going to run the system, but this time the two masses are going to be connected. And you can see I'm getting a much more complicated pattern. You can see, let me actually, yeah, now I'll just keep it like that. You can see we start off, mass 2 is displaced by a distance of 0.1. Mass 1 is not displaced at all. And mass 2 begins to oscillate, but as it's oscillating, its amplitude is decreasing, and some of the energy is getting passed over to mass 1. And you can see that this will be a periodic trend. So if I scroll up and I just increase the amount of time that we're watching the system, you can see it looks like the energy is transferring back and forth between oscillator number 2 to oscillator 1 to oscillator 2 to oscillator number 1. And you can even see that in the animation. Let me slow it down so it's a little bit more apparent. We'll go from the beginning. So you can see it. Mass 2 is oscillating. Mass 1 starts to oscillate. Mass 2 slows down. Then mass 2 starts to oscillate. Mass 1 slows down. And they couple back and forth, and they transfer energy back and forth between the two. And you can see, if I make that coupling even weaker, you can see it takes even longer for that energy to transfer back and forth. So we had a few cycles in, now we're only getting about 1 cycle in. And if I make it even smaller, you can see it takes even longer for that energy to pass back and forth between the two. So we can play around with this in a bunch of different ways, and I highly recommend, if you've taken the chance to copy down this code, that you play with it on your own as well. So we've tried switching up the spring constant and seeing what happens and how quickly the energy transfers back and forth between the two systems. Let's try plugging in some different values for x1 now as well. So I will keep mass 2 displaced by an amount 0.1. Let's see what happens if I also displace mass 1 by the same amount. So that's interesting. The two motions seem to lie on top of each other. In fact, let me go back. I'm going to decrease my my simulation time to get a better picture here. And we can see what's going on there. The two masses are moving back and forth in phase. And the spring in the middle is not being stretched at all. It's like it's not even there. If I just cut it off, these two masses are really only feeling a force from the springs on the outside, because the spring in the middle is not being stretched at all. The systems start in phase with a displacement of 0.1, and then they stay in phase for that whole for the whole lifetime. What happens if I put them 180 degrees out of phase? So let's say I still displace the second mass by 0.1, but this time I displace mass number 1 in the opposite direction, so that it is moving in the negative direction, so that the spring in the middle this time is being stretched. Well, we can run that, and you can see the motion starts out of phase. X1 starts at 0.1. X2 starts at 0.1. X1 starts at minus 0.1, and they stay out of phase for the entire lifetime of the oscillation. You can see that in the animation as well. You can see it's like it's breathing in and out and in and out and in and out, staying 180 degrees out of phase from each other. Now, it turns out that the two motions that we just looked at, when the oscillators were moving both in phase with each other, when the oscillators were moving either in phase or 180 degrees out of phase with each other, those are going to be what's called the normal modes of oscillation for this system. So the way to see that is through a variable transformation. So if we were to plot the system in its current state, and we're going to plot two things. We're going to transform from our variables being x1 and x2. We're going to transform those to being x1 plus x2 and x1 minus x2. So starting with the motion being 180 degrees out of phase, if I make this plot, let me actually put a plot legend in here. So for the first option, we have the system oscillating in phase, so that's x1 plus x2. And the second one, the second option we put in was the same thing, but x1 minus x2. And you can see that the out of phase system, which is what we have here, when the mass on the right is moving to the right, the mass on the left is moving to the left, and vice versa. You can see that in this mode, x1 plus x2 doesn't get any motion, but x1 minus x2 oscillates in simple harmonic motion. We can see the same thing for the other mode by putting them back in phase with each other. You can see they're now oscillating in phase. Masses are moving in the same directions at all time. And when I replot this, now the collective motion x1 plus x2 will get oscillatory motion. You can see the red curve, but the blue curve is now 0. The out of phase mode is does not have any motion associated with it. So we've got two motions. The masses are going in and out like a harmonica out of phase with each other, or not a harmonica. What's it called? The bagpipe, the instrument that you pump in and out. Somebody will tell me in the comments. So you've got the motion where they're going in and out of phase. You've got the motion where they're moving back and forth together in phase. Those are the different normal modes for this system. And if we transform this system to have, let's say, more masses or different spring constants, or change the mass so that one of the masses so that it's heavier than the other, then you can see that you will get, the problem can become a lot more difficult. And we want to show you how to solve that more general case and how you find the normal modes for a more complicated system than just these two masses connected by just a few springs. That's all we'll cover for today. Join us next time where we'll continue our analysis of coupled oscillators and we'll show you a more general way of conducting normal mode analysis. Thank you for watching. Click like if you liked the video, and if you'd like to see more of these, please click subscribe.